open for questions.
Thank you.
Thank you, Abhi.
So as a part of the session, we'll be taking more questions at the end. So we are getting the next talk is from Mount Sinai. Dr. Ankit Sakhuja is a director of artificial intelligence and informatics, Institute of Critical Care Medicine, director of clinical informatics research and division of data-driven and digital medicine. His introduction keeps on going. He's an old friend, and actually initially I approached him because I wanted to talk to him about the current status of artificial kidney, because he also have to have the previous experience of being a nephrologist. But with this current role, we realized that, okay, we can curate something about role of AI in vascular access. So he has actually curated this talk because as such, there is no talk which exists on this. He has to go through a lot. So thanks, Ankit. Great to see you after so many years. And all up to you.
Thank you, Himanshu, for the kind introduction. Good morning, everyone from New York City. It's an absolute pleasure to have the opportunity to talk about artificial intelligence in front of such an excellent group of clinicians. It's heartwarming to see artificial intelligence finding applications in newer fields within healthcare and such a burgeoning interest in artificial intelligence. So in this talk, I'm going to go over some of the basics of artificial intelligence, and then we'll talk about some of the very specific examples of studies, how artificial intelligence so far has been implemented in the field of vascular access. I'm gonna turn my video off just so that you can all concentrate on the slides, and please feel free to ask any questions as they come up. All right, so the first question is, why do we really even care about artificial intelligence? And the answer is simple, right? There are so many things in our daily lives that depend on artificial intelligence, from various appliances in our homes to the facial recognition software that we use to unlock our cell phones. Navigation apps that we use to get from one place to the other, to text editors, virtual assistants, chatbots, even self-driving cars, you name it, that all is built on artificial intelligence and shows how artificial intelligence has percolated our world. And it's not a surprise then that artificial intelligence is finding its ways into the realms of healthcare. But that really begs the question, what is artificial intelligence? Very, very simply, artificial intelligence is the science of making intelligent machines. Now, this is a rabbit hole, right? Question is, what is intelligence? Very simply, intelligence is the ability to learn from experience and apply that learned behavior to deal with new situations. So intelligence has many elements to it, as enumerated on this very busy slide over here. So we can say that artificial intelligence is the ability for a computer to think, learn, and simulate mental processes, such that it can independently perform complex tasks that once required human input. So now that we have that somewhat out of our way, let's talk a little bit more about what are the various types of artificial intelligence that are out there that are useful to us in the current times in healthcare. So if we look at all the artificial intelligence algorithms that are out there, we can put them in three buckets. One is machine learning, one is deep learning, and one is natural language processing. So let's unpack these a little bit now. What's machine learning? Machine learning is the technology that allows computers to learn themselves without the need for explicit programming. Now, that doesn't mean that we don't have to do any programming. That's what we do in our lab day in and day out. We program computers, but we don't have to spoon feed the instructions to a computer. And there are three types of machine learning algorithms that are out there. There are supervised algorithms, unsupervised algorithms, and then there is something called as reinforcement learning. So what's supervised learning? Let's say you have a basket of fruits. There are some apples in it, some oranges in it, some bananas in it. And you want the computer to separate them out into apples separate, oranges separate, bananas separate. What you would do in this case is show the computer that, this is what an apple looks like, this is what an orange looks like, and this is what a banana looks like. Now here, the important thing is, we are not telling the computer that, the apple is red, or its shape is this, or its texture is this, or the weight is this, or the dimensions are this. We're just telling the computer the final labels, that this is what an apple is, this is what an orange is, this is what a banana is. And then this algorithm figures it out that, the shape of the apple usually looks like this versus orange like this versus banana like this, or the color looks like this. So we are not giving or spoon feeding explicit instructions, but we are still providing some coding to help the machine learn. Now with this, what the computer can do is it can separate these fruits out. Pretty phenomenal. But what is even more interesting is that after this session of training, if you give this computer a new basket of fruits, which is, new data or validation data, it can do the same thing on that data, and it can separate those baskets of fruits out, which it has never seen before. One of the very, very simple examples of this supervised machine learning is regression analysis that we all know of. Very simply, the goal of regression is to find the best fitting relationship, which is basically just a mathematical function that describes how the independent variable influences the dependent variable, right? Like how does the disease acuity affect the length of stay in the hospital? Now, another example, which you will see a lot in machine learning literature, is something called as decision trees. Now, these decision trees, they create splits along variables that allow for the best discrimination between the classes. So the goal of a decision tree is to find the feature and the threshold. And feature is the variable. So the variable and the threshold of a variable that produces the most homogeneous groups. Say, for example, I want to go out and play cricket today in New York City. The first thing I'm going to do is, check the weather, right? And if the weather is cloudy, then it's a good day to play cricket in New York City. But if it's sunny, then I need to look at humidity. And if it is not too humid, I can go out and play. If it's too humid, then that may not be a great idea for me to go out and play today. I don't want to get all sweaty over there, right? If it's rainy, I need to see how windy it is. If it's very windy, then I cannot play. But if it's not that windy, I can play. So you can see that this becomes a tree of these decisions which split along different variables at different thresholds. So this is what a decision tree looks like. And we can make these extremely complex decision trees for a lot of things, for many things in healthcare, very similar to this very, very simple decision tree. But now let's say that, I want to play cricket in Lucknow, or I want to play it in Mumbai or Delhi. The problem with this decision tree is that this has been built according to the conditions of weather in New York City. So in a way, you can say that this decision tree is biased for New York City and may not work very well or may not generalize very well to how the weather is in Lucknow or Delhi or Mumbai, right? So what do we do in that case? There are two ways to handle that. We can create this multiple decision trees in various subsets of data. So say we have data from all these cities for weather, we can create these decision trees with all these different weather patterns. And we then take the final prediction as an aggregate of these results. This is something called as a random forest of trees, right? And this is again a very, very common machine learning algorithm that you will see in any of the machine learning literature. Another way to build these trees is where we build this decision tree, and every next decision tree is going to learn from the mistakes of the past tree in making these predictions. This is something called as gradient boosting of trees. And a very common example of an algorithm used for this is something called as XGBoost. So when you're reading through the literature of machine learning, you will come across some of these terms very, very commonly, but this is at the crux of what they mean. This is an example of how some of these machine learning algorithms have been used in literature. So this is a study from Mount Sinai where researchers wanted to identify accurately patients who are in the hospital and have malnutrition. Turns out it's not that easy to identify those patients in a hospital setting. So they used machine learning, and more specifically, they used this random forest classifier. What they did is they took these 5,000 some patients, split that data set of 5,000 patients into 70% for training and 30% for testing their developed algorithm, which is a very standard way of doing things in machine learning world. And what they found was that their classifier must plus, which was based on random forest, ended up performing much better than the must score, which was standard of care until that point. And now, since then, at Sinai, we use must plus to identify these patients who have malnutrition in the hospital. All right, so moving on to unsupervised learning. Let's go back to our basket of fruits. We have these apples, oranges, bananas, and whatnot, right? We still want the computer to sort these things out separately. But this time, we are not going to tell the computer what's an apple, what's an orange, what's a banana. We want the computer to figure it out itself, right? And as it turns out, using these unsupervised algorithms, and they're unsupervised because we are not giving any instructions whatsoever to the computer, it can still figure out in a very decent way that this is what one group of fruits is, this is what the other is, this is what the third is. What it cannot say at that time is that what is an apple, what's an orange, what's a banana, because it just doesn't know that, right? All it can tell you is that this red-looking pear-shaped fruit is this orange round fruit is this, and this elongated yellow fruit is this. So this is an example of unsupervised learning, which is used a lot in healthcare these days to identify heterogeneities in seemingly homogeneous populations. For example, this is a study from our group where we wanted to see if the patients who develop acute kidney injury are homogeneous group of patients or not in a hospital setting. And the researchers here found that there were actually 3 different subgroups or subphenotypes of patients who develop acute kidney injury. Not only were they different in terms of various lab parameters, they were also different in terms of outcomes. And as you can see, for both need for dialysis and mortality. What this can do is help identify these more homogeneous populations for various trial settings. And that's how slowly this machine learning technique is starting to be used to have a more enriched populations for trials at the outset. There are many other disease conditions in which this has been used, including sepsis, ARDS, etc. All right, finally, let's talk a little bit about reinforcement learning. So this is still a very nascent and more upcoming machine learning technique where the computer learns by directly interacting with the environment. So the computer learns just like you and me by trial and error, and it continues to get feedback for its actions. If its actions lead to an outcome that we like, we give it a positive feedback or a positive reinforcement. If it takes actions that lead to an outcome we don't like, it gets a negative feedback or a negative reinforcement, hence the name reinforcement learning. A very, I think, easy example to understand this is this little kid whose parents want her to go from this table to the chair, but takes take her first steps to go, right? So if that is the case, what would happen is this kid would get up and walk, right? If the kid does not fall, takes the correct steps, the parents would give her accolades, right? The kid will feel good about herself, take more steps, and get more accolades. Here, if the kid takes a misstep, the kid will fall and will get a boo-boo, right? And the kid won't like that. So that's your negative reinforcement. And the next time onwards, this kid will adjust her steps to make sure she doesn't fall. But if the kid continues to take the right steps, continues to get accolades, continues to get positive reinforcement, and that's how this kid will learn how to put her steps one after the other in this precise pattern so she doesn't fall and can get from the table to chair. And this is exactly how we code a lot of these algorithms in our lab, by giving these incentives to the computer to take the right action. Okay, so moving on to deep learning. This is something that is very, very commonly used, and a lot of terms get thrown around. So I'm going to try to introduce some of these concepts to everybody here. So deep learning is really built on the concept of artificial neuron. Just like a neuron takes inputs, processes them, and then comes up with an output, here we have an artificial neuron, or sometimes called as a perceptron. It takes these inputs, processes them, and comes up with an output. Now, if you look under the hood, artificial neuron is really nothing but a mathematical function. Here, each neuron takes an input, and then each input is multiplied by a weight. What is this weight? This weight is just a perceived importance of each input for that neuron, for that particular outcome at that particular time. And these are set at random. And that is why when we are doing deep learning, when we are developing these deep learning algorithms, you have to run hundreds, sometimes thousands of iterations to find those exact weights or perceived importances that the neuron should give to each input, to find the right mix of weights to predict an outcome, right? So for example, here, the second input becomes the most important one, and the third one, the least important one, right? At least in this iteration. Now, these weighted inputs are then added together to form a weighted sum, and this weighted sum is then compared against a pre-decided threshold. Now, this threshold decides whether the neuron should even bother firing or not, just like neurons in our body, right? If the neuron should fire, this threshold also has information built in about how the neuron should fire. It can have multiple different types of outputs, from 0 to 1, between 0 and 1, and we can spit out a probability function. So it all depends on what we are trying to achieve from this neuron at that point. Now, rarely is a single neuron helpful for anything, and same thing in machine learning. We usually need layers of neurons, something we call as very aptly multi-layered perceptron, or this is your classic artificial neural network. So in this, we have an input layer of neurons where the whole function of the input layer is just to pass the inputs to the hidden layer where all the analysis happens. Now, once the analysis happens in the hidden layer, that passes on the output to an output layer, and then we see the output on our user. If there are two or more hidden layers, that's when we start to call it a deep neural network. So deep neural network is nothing but a layer of perceptrons where there are two layers that run analysis, called as hidden layers. But rarely are things so simple in healthcare, right? In healthcare, we have another layer of complexity in our data. Our data is time series, which means that in this data, we have multiple time steps, and the outcome at each time step depends not only on the input at that time step, but also what happened at that time during the previous step. For example, say someone in the ICU has hypotension, right? And I'm making a model to predict their mortality. Yes, their blood pressure at that time point will be an important variable in predicting mortality, but say I go in and give them a medication to raise their blood pressure. In addition to the blood pressure, the response to that medication will also be an important part of the equation. right? So in addition to what their blood pressure is now, I also need to know what happened when a minute back I gave them a medication. How did they respond to their blood pressure? Now, this temporal relationship cannot be effectively captured by this artificial neural network that I just showed you. So this is where we use special models where neuron gets input not just from the input layer, but also from itself at each time step. And this is what we call as a recurrent neural network. Now, in AI world these days, we have a lot more fancier models also. So this recurrent neural network has this very short memory of what happened at the last time step. But we have models now which can have a longer memory, something called as a long short-term memory network. There are these transformer architectures out there which are used in things like ChatGPT, right? Which have even longer memory context built into them. Another type of data that we use in medicine is imaging data, right? But if you think about it, all images are made up of these pixels, right? So we use these deep learning architectures called as convolutional neural networks or CNNs to review these images. What these CNNs do is they use this filter or, which is a magnifying glass to scan the image few sections at a time and just looking for these specific patterns, right? So it'll just keep scanning and all it is doing is trying to look for specific patterns. Once this filtering step is done, the CNN shrinks down this information further with a pooling step to really try to hone down on what is really important in this image, right? And a CNN has multiple layers of this filtering step and this pooling step. And once all this is done, with every step that is coming up, it builds upon the patterns discovered by each previous layer. And ultimately, it creates a comprehensive idea of what the image is. And for example, in that chest x-ray, it can tell you whether the image was normal or abnormal. And this is, something very similar to what you would use. Say if you take pictures of AV fistulas, and you want to see if there is a problem with the picture of the AV fistula or not, this is the AI technique you'll use, and I'll show you an example of this later in the talk. Now, finally, I think we need to talk a little bit about natural language processing because that is the big buzzword these days, right? Very, very simply, natural language processing is where we train the algorithms to understand, interpret, and generate human language. And they have come a long way. Let's take an example. So these are 3 sentences. My dog's name is Tiger. He has golden fur, and he's a golden retriever, right? Not too long ago, the natural language processing, all that could do was to count the number of words in the sentence. Then it took a little while where it could start to learn to capture these semantic relationships, where it could tell that, golden and tiger look like they are somewhere close together. And now these natural language processing algorithms can understand that, tiger is the name and golden is actually the color of the fur. It's not a name, but it's the color of the fur, which is pretty remarkable if you think, right? Where are all these NLP applications used? One of the prime examples is text classification, where it can categorize text into predefined classes. A very good example of this is the spam filter in your emails. We use it for natural language generation. With over 2/3 of information being unstructured data, it's very useful in retrieving unstructured information. And then, analyzing the sentiment of text messages. That is very important for a lot of companies, right? For brand reputation management. We can understand the sentiment of the populations with this, right? So very powerful techniques. All right. And then with how important large language models like ChatGPT have become in the last few years, I think we need to talk a little bit about them. So what are large language models? They offer a very comprehensive approach to language tasks. Large language models have this fluency, which is beyond your traditional natural language systems, right? Why is that? Because they are trained on vast data sets from a diverse sources, as you can see on the left side of the screen. These different types of data are then fed into this large language model. where during the training phase, like any other AI model, the model learns to understand, interpret, and make predictions based on the data it has seen. After this, the model goes through a phase of adaptation, where it adjusts to perform these some very, very other specific tasks, as you can see on the right side of the screen. Now, these LLMs, they are a result of an amalgamation of deep learning and natural language processing, and a very good use case of the use of transformers, which can handle the sequential data very well while assessing the significance of each word that comes over there. And this is a prime example of how large language models can be used in healthcare. In this study from Stanford, researchers showed that you can summarize parts of the patient charts very effectively, even better than humans, when using these large language models. All right, so let's talk a little bit about how AI has been used in vascular access. And here I have picked some very specific cases to show you how in different ways it has been used and could potentially be used with your guys' help. So this is an example of a study where the authors wanted to identify AV fistula failure using artificial intelligence. So they used 13,000 some patients from a European clinical database, and all patients had mature fistula at least for 3 months. And they said that, we are going to identify AV fistula failure if somebody switched to a different access, there was occurrence of a procedure aimed at reestablishing patency, or there was any hospitalization due to complications related to the fistula. They used, very normal set of variables, something that, we'll call as structured variables that are very easily available in any Excel sheets, right? They took their data set, split it into 70% for training, 30% for validation, which is again very standard in machine learning world. And they developed this model to identify AV fistula failure. And as you can see over here, the model's performance was really good. So what this shows you is that using relatively routinely collected parameters that were available in a large registry, the authors could use machine learning to identify AV fistula failure in these patients. It's pretty remarkable. Now, another thing that the authors in this study were able to battle was the seemingly black box nature of artificial intelligence algorithms. That is a lot of reservation with artificial intelligence algorithms, that we don't know what the machine is thinking and how it's making decisions. A way to do that is that we look a little bit under the hood to see what variables is the machine giving importance to. And we can generate a set of variable importance or a feature importance graph, if you will, where we can see that what the machine is thinking. And this helps us understand what is really going on in these algorithms and maybe refine them and maybe even allow them to start to think a little bit more like how we would make decisions. Now, this is another example of a study that used artificial intelligence. So here, what authors did is they used an electronic stethoscope to procure sounds from AV fistula. The first position was at the arteriovenous junction. And then after that, the positions were spaced about 3 centimeters apart. And then they used deep learning to analyze these captured sounds to identify the stenosis in the fistula. And as you can see over here, they were able to build a pretty decent model using the captured sounds and deep learning. This is another example now where the authors used a very different kind of data. So far we have seen that they use structured data. We've used sound to analyze using artificial intelligence. Here we are using waveforms. So they use plethysmograph sensors, put them on the fistulas, and use those waveforms that are generated from the plethysmographs and fed them in the CNN model that we had discussed, to identify what the quality of the graph was, and were able to classify the quality of the graph in 5 different categories from poor to excellent. And as you can see over here, the performance of this model was also pretty decent, right? And then finally, this is another kind of application of artificial intelligence in the field, where this time authors enrolled patients from 20 different clinics across US, and they took pictures of their AV fistulas and fed them through the CNN model and tried to see if the model can identify advanced aneurysms. And as you can see over here again, that the model was able to identify advanced aneurysms with much ease, right? So you can see that artificial intelligence has been used to process structured data, waveform data, imaging data, even sound data to make decisions about vascular accesses. This is still, I think, only scratching the surface, though, because there can be many potential applications of AI in this space, right? From identifying what type of access is best for a patient to determining maybe even optimal timing or treatment strategies for various complications. Thank you.
Thank you, Ankit. I know that some of the initial part might have been slightly over the head, but I'm telling you, I tried to learn about how the AI works, and this was one of the most simplified talk I've ever seen. So I think even in the history of AI explanation, at least in our field, I'll be putting your talk as one of the landmark. So thank you for that.
Thank you, Manju.
If any questions from audience, because I think there's a role. I think we discussed about, and a lot of papers have been coming about prediction of and finding the AV fistula stenosis, because in the entire audience will agree that if one thing we want, if we can find a stenosed fistula in time, we can save it. Okay, if we fail to do that, fistula gets thrombosed, outcomes are totally different. And this is just one of the area where we can actually have the AI looking in the future. I saw one of the paper in Nature where they use the sound models from the sound outputs from the stethoscope and putting those as a feedback for the AI model. So thank you. Thanks a lot, Ankit. And we'll continue with this.
Thank you, Manju, for having me.
Thank you. So I think there's a one talk remaining for the session.
Yes.
We'll, because of time, we'll be continuing session even after this. The tea will be served inside. So that's just to save the time.
Coming back to the presentations here, so next talk is going to be